So for scenarios where we want to find the sample linear correlation and evaluate the association between the two variables, we're going to use technology to find that value for R, since calculating by hand is very difficult and may lead to some calculation errors. So what we're going to do is we're going to Stapplet. So when we go to Stapplet, here's our home page here. Under data analysis, we're going to two quantitative variables now, since we have two columns of data. And when we're there, it wants some information. So the explanatory variable, that lines up with our X values. So those are inputs to the equation. It's kind of like usually what's given. And then response is our Y values. So it's usually the thing that is responding to the explanatory variable. So X and Y, and we're going to put names of those variables down, and then we're going to plug in the observations. We can separate them with a comma or space, but just make sure that you are lining things up correctly here. So I actually typed everything in already, so I'm going to jump over to this other window, and here I put temperature, and here I put chirps per second, since we are suspecting that the crickets are responding to the temperature outside. Here's the temperatures, and here we have our cricket chirps per second. And then we could just do a rough check that things are lining up with each other. It's not a perfect system to see how it lines up, but it's the best we can do. Okay, then we are going to select Begin Analysis. And first thing it's going to do is it's going to give you the scatter plot. What's really nice about the scatter plot here is it's kind of interactive, meaning you can look at individual points. So where I'm hovering right now, it says temperature 89, chirps per second 20. So it's essentially giving me the coordinates of that point. And if we fill in the names of those pieces, it's actually telling us kind of in context what's happening with temperature and chirps per second. And it'll label our axes for us, so it produces just a really nice scatter plot for us. Then what we're also interested in is down below here, which is calculate correlation, and that's just a button to click right there. We click that button and it gives us R right there. So R is a 0.8135. We will go on to calculate least squares regression line, but we'll do that in a separate video. But for now, we stop right here at this little button, calculate correlation. So going back to temperature and chirps per second, what is the correlation between the number of chirps per second with crickets and weather? And with that, we got R equals 0.8135. So something to note here, how it's asking the question is just what is the correlation, and R is our value for correlation. All right, write a brief description of association. So this wants two pieces of information. When you see association, we want to think strength and direction. So we want to describe those two pieces in context of our two variables. So how we do this, we take our value for R, so that 0.8135, and what I'm going to do is I'm going to take that value and take it to that number line. So 0.8135 is right here, which means my lines don't line up nicely. Imagine that it's going through strong and positive. So we have an increasing relationship between these two variables, and the relationship is strong. So I want to make a sentence describing that. So let's go with the association. Between chirps per second and temperature is strong and increasing. You could substitute in the word positive there too, but increasing kind of shows a nice relationship that as one's getting larger, the other one's getting larger as well. So that's how we would write a description of association between the two variables. We could name them, and then you should be talking about two things: strength and duration. Do these results confirm that the increase in temperature leads to a higher number of chirps from crickets? Explain. So the wording here. We see one thing increase and that leads to the other. This is claiming causation. This is saying cause and effect. One thing gets larger so the other thing does, and we don't know that. No. All we can say is there's a strong association. But we can't make claims of cause and effect here. So a kind of theme you'll see in this section as we go and make sentence conclusions and make interpretations, we kind of want loosey-goosey wording in there. Like, we don't want to say this does that, but we'll say like the association, the relationship between, there tends to, we can predict. So we don't know anything for 100% certainty with these claims that we're making, but we have an idea of the trends is the idea. And with this strong association, we can be more confident in those trends. Whereas if R was like 0.4, we could talk about these associations, but I would want to be very, very careful of them. But the stronger it is, the more strong we can feel with our conclusions that we're making. Okay, next up, coefficient of determination. I love saying this one because it just sounds scary, but it's not bad at all. It is literally just equal to R squared, meaning we take our value for R and we square it, and that's it. But we can do a little bit extra in terms of interpretation with it. That's kind of the tricky part with it. So the coefficient of determination tells us the percentage of the variation in the y values that can be explained by the least squares regression line of y on x. And actually, I want to rephrase that. So that is a typical definition of coefficient of determination, and how I just kind of want to give you a framework for fitting a sentence together. So R squared is going to be interpreted as a percentage. So it's the percent of the variation in y that can be explained by x. So when I need to make an interpretation of the coefficient of determination, I think about this kind of sentence structure and filling in three pieces. I want to fill in the percentage, I want to fill in what y represents, and I want to fill in what x represents. And maybe after that, I reword it one more time if I need to, but really this sentence structure can get at the idea of it. And just to kind of preemptively note, there is a myopen math question that will sometimes refer to this not as a percentage, but as the fraction. But a percentage is a decimal, is a fraction. They're all interchangeable with each other. But I just wanted to kind of mention if there's a question of like, what is the fraction of variability? The wording's all there, but sometimes the fraction bit can trip up students. So fraction or percentage of the variation in y that can be explained by x. So let's try this out. So going back to our example, not from last class, but from our last example, we found r is 0.8135. So I want to find r squared. And just as a reminder, when we plug in values to be squared, make sure you use parentheses. It is not too bad in this case because we have a positive number, but if r is negative, basically no matter what, you should be getting a positive value out for r squared. So we want to put 0.8, 0.135 in here and simplify with a calculator, and that's going to be a 0.6618. So my interpretation, I would say 66.18% of the variation in chirps per second, or let's even, I'm just going to say cricket chirps. In cricket chirps can be explained by temperature. So this really is just another way of kind of explaining the strength of the association. So what this is basically saying is, with the cricket chirps, there's a variability occurring. There's a change happening. And that change and how it's changing, 66% of that change is coming from temperature. Which means we're estimating that 34% is coming from other things. Is it mating season for the crickets? Is there a predator out in the woods that they hear and they're sending out alert? There could be all sorts of other things that affect cricket chirps, but from this relationship and seeing this association, the coefficient of determination tells us the percent that's coming directly from that other variable. So what we're going to see is the strength is going to line up with this kind of percent relationship between the two. Meaning if we just kind of go to extreme cases here, like if r is equal to 0, then r squared is going to be equal to 0 as well. And with that, it would be this idea that 0% of change in y comes from x. Meaning there's nothing, they're not relying on each other at all. So it kind of interprets the same thing. And then if we have the strongest association, like r equals 1, well, if we square 1, that's still just 1. So that would mean 100% of change in y comes from x, which makes sense because if it's perfectly linear, they are 100% relying on each other. As x goes up one little bit, y has to respond, and there's no other outside factors. So that's coefficient of determination. My last little piece I just want to emphasize is don't mix these up. If I ask for correlation, I want r. If I ask for coefficient of determination, then it's r squared. Sometimes these names get mixed up for students, so just be careful and just keep in mind that correlation can also be called the correlation coefficient. So coefficient is a term that will show up in both, but seeing determination makes it r squared.